Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If you're looking for the ultimate shortcut into the thermal design of heat exchangers, well, this deep dive is definitely for you. We are pulling back the curtain today on the core mechanisms of heat transfer optimization. Specifically, we're focusing on how engineers manipulate fluid flow, geometry, and surface forces to really maximize efficiency during condensation. And that's, a non-negotiable process in everything from your air conditioning unit right up to your utility scale power cycles.
Right. And our mission today really is to uncover the specific physical levers that high-performance engineers are actually pulling to boost thermal performance. We've synthesized quite a stack of sources covering the whole gamut. The fundamentals of condensation physics, detailed flow regimes inside tubes, advanced passive techniques like microfins, cutting-edge active enhancement using something called electrohydrodynamics or EHD, and even the crucial role of surface material science itself.
Okay, let's unpack this then. Maybe we should start right inside the tube where the condensation actually begins. When I talk about two-phase flow in horizontal tubes, I understand there's this constant kind of fundamental conflict playing out. It's a battle between gravity pulling the liquid down and the vapor shear trying to strip it away. How does that conflict, how does it define how well the heat exchanger actually works?
Well, it pretty much defines everything because the distribution of that liquid condensate, that's your single biggest enemy for heat transfer. What we call two-phase flow, it gets dramatically reorganized just by changing the speed of the vapor core. So think about it. When the vapor velocity is low, gravity just wins easily. The condensate pools at the bottom of the tube, and that creates a thick insulating layer. We call that stratified flow.
And insulation is exactly what you don't want. It's the enemy of heat transfer.
Absolutely, it's a barrier. But okay, once you start increasing that vapor velocity, the shear forces, the drag, essentially exerted by the fast-moving vapor, start to overcome gravity, at least locally. This pushes the liquid around the tube wall, and you see this transition sequentially. It goes into wavy flow, then wavy annular flow, and eventually you hit the prized regime, annular flow.
Right, annular flow. That's the goal because the liquid coats the entire wall, but as a thin film, right, minimizing that insulating layer.
Precisely. A thin, evenly distributed film is what you want, and the flow regime directly determines the efficiency. Our sources highlight something quite interesting here. Your heat transfer coefficient, dollars, it actually becomes pretty insensitive to the flow speed or mass flux when the flux is low. Let's say around $75 tex kilograms per second per meter square.
Insensitive. Why is that?
Well, it's because gravity is just dominating how thick that film is at the bottom, almost regardless of how much vapor is actually flowing through the core. The geometry of the pool is set by gravity.
Okay, that makes sense. But once we cross some threshold, maybe get that vapor moving faster, and we're driving this fast annular flow, then the heat transfer suddenly cares a lot about speed. It becomes highly dependent on mass flux and quality.
Yes, exactly. For example, the sources point to mass fluxes like $300 tex kilograms per second per meter squared and above. At that point, you're firmly in forced convection territory. And here, the heat transfer coefficient, different dollars, is shown to be proportional to the square root of the pressure drop gradient. That's the square root of minus delta P divided by delta Z, or delta P delta Z. Ah, okay. So that mathematical relationship tells us something immediately important, doesn't it?
The heat transfer gain is directly proportional to the resistance and friction we're generating. It sounds like the harder the flow has to push, the more effectively the vapor shears that liquid film, thinning it out, and the better the performance gets.
That's exactly the mechanism. The friction is the enhancement in a way. But, to really appreciate how much enhancement we're talking about with these methods, we need a baseline. What happens if we just let gravity do its thing? And that's where the classic Nusselt analysis for gravity-driven film condensation comes in. It sets that sort of foundational limit.
Right, the Nusselt equation. It looks pretty complex when you write it out. It's 180.7299 times the fourth root of a whole bunch of terms. Can you maybe unpack what that famous equation tells the listener conceptually, especially about the levers we can't easily change?
Sure, let's break it down. It's 10.7299 times the fourth root of the quantity. Rho sub L times G times rho sub L minus rho sub G times K sub L cubed times lambda, all divided by mu sub L times T sat minus T sub W times D sub O. Phew. Okay, what does that mean? It's all about the natural physics of the situation. That equation shows that the theoretical limit of gravity-driven performance is entirely set by physical properties and conditions. Things like liquid density, mu sub L, gravity G, liquid thermal conductivity, K sub L, the latent heat of vaporization, lambda, and the liquid viscosity, mu sub L. plus, of course, the temperature difference between saturation in the wall, T sat minus T sub W, and the tube diameter, D sub O. These are mostly inherent properties of the fluid and the setup. So the point is, if we want to exceed this inherent baseline performance dictated by gravity, we'd have to stop relying solely on gravity. We need to actively interfere with the physics.
Okay, so interfering. If we can't always just crank up the vapor speed to force that efficient annular flow, maybe due to pressure drop constraints or something,
Yeah.
we need to look for other physics we can interfere with, perhaps passively. And that brings us to this kind of counterintuitive world of tiny fins. We're talking really small fins here, less than 1.5 tex millimeters high.
Yeah.
Why are we deliberately keeping the fins low? Isn't the standard heat transfer rule just add more surface area? Bigger fins better?
That's the classic thinking, more area is always better. But for condensation, the goal with these low fins is radically different. It's quite clever, actually. We aren't just adding area. I mean, there is some area addition, but that's not the main point. We are specifically engineering microscopic pressure gradients, and we're using surface tension drainage forces to actively thin that insulating liquid film.
Surface tension drainage forces. Okay, so it sounds like we're turning the liquid into a sort of self-squeegeeing system. How exactly does surface tension achieve this drainage? That seems subtle.
It boils down to curvature. The physics is described by Laplace's equation. Essentially, any curved liquid-vapor interface creates a pressure difference across that interface. The equation states that the pressure difference, sub L minus pi dollar G, is balanced by the surface tension, sigma, and the radii of curvature of the interface. Let's call them Cora 1 and Ori 2. So Paulo PG, all is sigma. 1 R 1 plus 1 R 2.
Okay, so the pressure difference changes depending on how sharply curved the interface is.
Precisely. The smaller the radius of curvature, meaning the sharper the curve, the greater the pressure difference generated. So engineers very carefully design the fin geometry, the shape of the fin tip and flank, so that the liquid interface curvature decreases as the liquid flows along the fin's path, from the tip down towards the base or trough. This intentional decrease in curvature generates a pressure gradient. It literally sucks the condensate from the top of the fin down into the troughs between the fins. This action keeps the primary heat transfer surfaces, the fin tips and upper flanks, covered by a much thinner, less insulating liquid film.
Ah, I see. This is where geometry optimization becomes a real art form then. Our sources mention specific profiles, like the Adamic profiles from back in 1981. These are sort of convex shapes designed specifically to maximize this surface tension pull, right?
Exactly. Those profiles were early examples of really trying to tailor the shape for drainage. And the results, well, they prove the concept works beautifully. If you compare, say, a standard trapezoidal integral fin tube to a highly optimized sawtooth fin geometry, the sources show sawtooth tubes can achieve approximately twice the condensation heat transfer performance.
Wow, twice the performance. And that's mainly from better drainage, not just the area.
That's the key insight, yes. The performance increase comes primarily from these superior surface tension drainage mechanisms, much more so than just the modest increase in surface area.
Okay, and to make sure that this microscopic squeegee effect is actually working and that gravity isn't just overwhelming it, especially between the fins, engineers use something called the bond number, or BDDDF.
Right. The bond number is our critical quality check for this strategy. It's defined as the ratio of gravity forces to surface tension forces. For our surface tension drainage strategy to really dominate and be effective, the bond number must be small. This metric basically tells you how tall the fin can be. If the fin height gets too large, the distance the liquid needs to be pulled becomes too great. Then the surface tension pressure gradient kind of dissipates before it can effectively drain the film all the way down, and gravity starts to win the battle again, pooling liquid between the fins.
Fascinating. So we've covered the forced approach, high-velocity annular flow, and this elegant passive approach using geometry-driven surface tension. Now let's move to what sounds like the most aggressive method of all, active enhancement using electrohydrodynamics, or EHD. Here, we're ditching the finesse and actually starting to apply external energy, right?
Yeah, EHD is fascinating, and it's definitely more energetic. It uses a high voltage but typically low current electric field to actively manipulate the condensate film. Maybe think of surface tension drainage as gently coaxing the liquid away, like using that microscopic squeegee we talked about. EHD, on the other hand, it's more like literally zapping or pulling the condensate off the surface using electrostatic forces generated by the high voltage. It can be a bit of a sledgehammer approach, but it can be incredibly effective.
A sledgehammer.
Yeah.
Okay. And it requires specific conditions, doesn't it? It doesn't work for everything.
That's correct. It really needs fluids that have low electrical conductivity. Dielectrics, essentially. That's
Mhm.
why it's most often studied and applied with refrigerants, which often fit that bill. The impact, as you hinted, can be massive. The reported enhancements for film condensation on a flat plate, for instance, can be as large as an incredible $2,000 tax process.
1,000%. That's extraordinary.
It is. And even for smooth in-tube condensation, which is often harder to enhance, the enhancement can reach up to about $6.555 times the baseline performance without the electric field. Huge gains.
But presumably, getting that kind of gain isn't just a simple matter of turning up the voltage dial. The sources mention a correlation for a refrigerant like R404A, and it looks complicated.
Oh, it's definitely not simple. It's a really complex, multivariable correlation they developed. The enhancement ratio, 1:2, it looks something like $1 plus C times N2 to the power $1 to the power $1 to the power gamma 2 times 10 to the power 2 n's to the power n, where 2 or 5. So what does that tell us? The conceptual takeaway is that the enhancement, that boost you get, depends on really complicated interactions. It depends on the electric field parameter related to voltage and geometry, the total mass flux, how much vapor is left, which relates to the quality and YEPTOP, and even the Jacob number, which connects latent to sensible heat effects. You're essentially fighting, or rather manipulating, flow dynamics, phase change physics, and the electric field strength all at the same time. It's a big optimization puzzle.
Right, a complex interplay. Okay, so to kind of round out our view on optimizing these surfaces, we should probably acknowledge that all these sophisticated methods, flow control, microfins, EHD, they all sit atop a foundational material science layer. We often assume in our models that surfaces are perfectly ideal, maybe optically smooth, but reality is different, isn't it?
Absolutely. Real-world surfaces are almost always altered by things like oxidation, maybe some roughness from manufacturing or use. And those factors can matter quite a bit, even if you think you're primarily focused on convection. Take roughness, for example. A surface is only truly optically smooth if the scale of its roughness is much, much less than the wavelength of the electromagnetic radiation interacting with it. As roughness increases, reflection becomes less specular, less mirror-like, and much more diffuse or scattered. And that dramatically changes how the surface exchanges heat radiatively.
And you also mentioned the subtle role of surface layers, especially things like oxide films. They can potentially sabotage performance, even if they're very thin.
Yes, that's a critical point, often overlooked. A very thin, non-metallic layer, like an oxide film that naturally forms on many metals exposed to air or certain fluids, can severely decrease the overall reflectance of the metal substrate underneath. And if reflectance goes down, absorptance goes up. Since many heat exchanger designs implicitly rely on the metal's high reflectance to minimize unwanted radiative heat loss or gain, adding even a thin, non-metallic layer can unexpectedly shift the whole heat exchange balance in a way you didn't intend. It really emphasizes that optimizing a condenser surface requires a holistic view. You have to consider all the thermal modes together: conduction, convection, and radiation, and how the surface material influences all of them.
This has been a really comprehensive look at the physics engineers manipulate for condenser optimization.
Yeah.
Let's just quickly recap the four main engineering levers we've identified for you, the listener, today.
Okay. First, we talked about controlling the flow regime. Really understanding and managing that critical balance between gravity and vapor shear, ideally to force high-efficiency annular flow when possible. Second, there's passive enhancement through geometry, using those clever microscopic fins to harness surface tension drainage, driven by carefully engineered curvature. Third, we looked at active enhancement, bringing in the big guns with high-voltage EHD fields to aggressively remove those insulating condensate films, leading to potentially tremendous performance boosts. And fourth, remembering the foundation, fundamental material surface control. That means meticulously managing things like surface roughness and those thin oxide layers to ensure you have the optimal thermal and radiative properties for the job.
Right. And ultimately, it seems the most efficient design you're likely to encounter in advanced applications is probably some kind of hybrid, isn't it? Maybe utilizing that passive geometry and the microscale surface physics from the fins, possibly augmented by active fields like EHD where appropriate. But I think the takeaway from the researchers who classify these flow regimes is really crucial. Different physical forces tend to dominate different regimes and transitions.
That's the real challenge, and maybe the final thought. Since these competing forces, gravity, shear, surface tension, maybe even electric fields control different transitions, like the shift from stratified to annular flow or how liquid drains, we should probably never expect a single, simple formula or parameter to perfectly predict all thermal behavior in every conceivable condensing environment. It's a constant reminder, really, that high-performance engineering, especially in thermal fluids, is often about understanding and managing complex, sometimes conflicting physical phenomena.
Until the next equation, design junkies, we are mechanical engineering made simple.